Corrosion and its prevention are a very practical application of redox theory. As you can see here, we have the hull of a ship. Well, ships and pipes and storage tanks, these things are primarily made of steel. And the main component of steel that we'll be concerned with would be iron. What happens to the iron? Well, it rusts. But you'll notice here, in this example, in this picture, you have these little metallic looking silver add-ons. Those are little plates of zinc, and those actually prevent the corrosion. Okay, so let's take a look at the main reactions involved. Well, when metal's sitting around, it rusts. That's what corrosion is. And when we think of rusting, we typically want to consider, why is it rusting? Well, it's because of the reaction with the air and the water. Okay, it's not just air itself. And when we think of air, we often want to think just oxygen. Okay, but it's not just oxygen. It has to be oxygen with water. And sometimes you can have oxygen with acid rain, which in that case you would have H+. So, as we said, primary reactant is oxygen and water. If you look on your redox table, you'll see that it is a oxidizing agent. Not a very strong one, but strong enough. The SRA would be the metal that's being corroded. It doesn't have to be iron, but when dealing with steel, it will be. So you can see here, we have the iron losing electrons to form the iron 2 ions. The oxygen and water are gaining electrons. So we have a gain of electrons, we have a loss of electrons, we have redox. And there's your net reaction. Well, we don't want this to happen. As we know, rusting weakens the metal and inevitably destroys it. Some things that can increase the rate of corrosion would be more oxygen around, which would be at a lower altitude. So in the mountains, high up in the mountains, you'd have a lot less corrosion than you would at sea level, for instance, given all the other conditions remain constant. The higher the humidity, you'll have more corrosion. So near the coasts, for instance, east or west coast, you would have a lot more rusting than you would here. Number 3, presence of electrolytes. Well, if you don't have a solution around to help carry ions, like for instance salt in the case of the coasts or salt on the roads, then you wouldn't get any corrosion. But that stuff's around typically. And we mentioned before, if you have H+ around, oxygen can act as an oxidizing agent as well. Well, H+ comes from a low pH environment, which we would like to think is more industrialized area, thus the acid rain. Okay, so that's rusting. You guys are all familiar with rusting, and those are the reactions involved. But how can we prevent it? There are a number of theories, but essentially what we're trying to do is prevent the iron from being oxidized by the oxygen and water. A number of very basic things you can do: just coat your material, whether it be with paint or plastic. Many pipes are coated with plastic polymer that simply prevents contact with the environment. Anything that will prevent contact with the environment will do. Then some other things that we'll look at a little more closely are these. They're all essentially involve the same idea. Okay, we're causing or allowing the iron, if it's in fact steel, to not be oxidized. We'll look at right now sacrificial anode. Sacrificial anode is exactly what it sounds like. It's an anode that sacrifices itself. Well, an anode is a reducing agent. And so your iron is acting as a reducing agent when it's being rusted. Well, if we're going to have an anode sacrifice itself, it must be stronger than the iron. Okay, so it has to be a stronger reducing agent than iron, or whatever you're trying to protect. Which means lower on the table. lower on the redox table. Okay, so there's our boat again. So which ones will we pick? You have a lot of choices. There's magnesium, zinc, aluminum. Those are very typical. Things you're not going to typically see would be elements from group 1. Okay, why? Because they're too reactive. Okay, it would be bad choices. And sometimes people will pick things like a gold or silver. Well, they wouldn't be good for a sacrificial anode. One, because they're above iron in the table, and secondly, they're just too expensive. So you also want to consider cost and availability. You don't want to paint your boat in gold unless you're really well-to-do. Okay, so basically all the sacrificial anode does, by incorporating that zinc or magnesium or what have you, you basically take the anode, the iron, the original anode, out of the picture. Okay, it's gone. So therefore, your iron won't rust, the zinc will rust. And if we go back to our picture, notice these are tiny little plates. Well, those can be easily replaced. Okay, relatively low cost and relatively easily. A lot easier to do that than replace the entire hull of the boat. Another theory is cathodic protection. Very similar, but instead of adding a sacrificial anode, a different metal, you actually use an electric current and force the current to the iron, to the steel hull or steel pipe, which therefore turns into a cathode, which, as you may recall from from earlier in this unit, electrons will always want to go to the cathode, and reduction takes place to the cathode. Okay, and that is harmless to the iron.